All right, let's dive right into this explainer. Today we're going to break down the massive, and I mean absolutely massive, acceleration in our ability to decode human thought. We're looking at the actual mechanics of brain-computer interfaces, BCIs, and how neural decoding is rapidly shifting from what used to be pure science fiction right into our absolute reality.
Just to give you a sense of exactly how incredibly fast this field is moving right now, consider this. In 2024 alone, researchers published over 14,000 peer-reviewed papers on brain-computer interfaces. 14,000! If you do the math, that is roughly 38 brand-new papers dropping every single day. So yeah, this is definitely not some slow-moving academic trend. It is a total explosion of data, discovery, and engineering that is literally rewriting the rules of what the human mind can do.
So here is our roadmap for today's explainer. First, the neuroscience gold rush. Then, decoding the brain's hardware. After that, translating thought to command, followed by restoring human movement, and finally, the neuroethics frontier.
All right, Section 1, the neuroscience gold rush, the explosion of BCI research.
So there are essentially dual engines driving this whole field forward. Like we just talked about, it's not just those 38 academic papers coming out every day. Over on the commercial side, things are wild. We're seeing the launch of brand new consumer-ready EEG headsets, and at least 3 different companies have recently shown off non-invasive BCIs that can pull off feats we thought were total science fiction literally 5 years ago. Plus, when you factor in federal mandates and massive philanthropic accelerators pouring money in, the race to map and actually interface with the brain is moving at breakneck speed.
Moving on to Section 2, decoding the brain's hardware from macro to micro.
Okay, so the absolute core hardware breakthrough of our current era is something called the Neuropixel. Basically, these are highly advanced devices capable of recording from hundreds of individual brain cells simultaneously. They were developed through these massive institutional collaborations, and these tiny probes finally allow scientists to capture the brain's crazy complex electrical and chemical signals at a completely unprecedented scale. It's kind of like trying to understand a city's traffic by listening to just one single car. Well, Neuropixels let researchers monitor the entire highway system of the brain, all at the exact same time.
And this specific hardware creates a bridge between 2 wildly different architectures. On one hand, we've got the biological brain, which, fun fact, operates at an estimated exaflop of processing power, but runs on roughly 20 watts of energy. That's basically the power of a dim light bulb. It's messy, it's highly intricate, running on all these electrical and chemical signals firing across billions of neurons and synapses. But then, on the other hand, you have the digital interface. Sleek, perfectly structured hardware. Think 8-channel consumer EEGs utilizing your standard JavaScript and Python developer kits. The massive challenge here, and really the great triumph of modern neurotechnology, is finding a way to seamlessly connect these 2 completely different worlds.
Which brings us to Section 3, translating thought to command, the BCI Rosetta Stone.
Bridging that gap requires a super precise translation process. It pretty much always starts with neural intention. The user wants to move a cursor or maybe speak a word. Next up is signal capture. That's where hardware, like those Neuropixels or flexible EEGs we mentioned, actually pick up the firing neurons. Step 3 is honestly where the magic happens. Algorithmic decoding. This is where machine learning steps in and acts as a sort of Rosetta Stone to decode the very syntax of human thought. And finally, step 4, we get the digital output. The cursor moves on the screen or the robotic arm lifts. Every single BCI out there relies on this exact pipeline.
But you might be wondering, why is this working so much better right now compared to, say, a decade ago? Well, it's because neural decoding algorithms have recently improved by double-digit percentages. It's huge. The integration of artificial intelligence is completely transforming our ability to decode these massive data sets of brain signals, doing it faster and way more accurately than ever before. It creates this incredible feedback loop, really. Biological principles are actually inspiring new AI architectures, and then those advanced AI models are in turn being used to decode the biological brain.
All right, Section 4, restoring human movement, clinical realities. The coolest part is that this is no longer just laboratory theory. BCIs are actively being deployed out in the real world. For example, in stroke rehabilitation, they're being used to help restore lost motor functions, sometimes by pairing them with tactile stimulation devices. For patients with ALS, BCIs are restoring communication, literally allowing completely paralyzed individuals to speak through computer interfaces. We are also seeing deep learning models predict and localize epileptic seizures with just stunning accuracy. And of course, there's the integration of mind-controlled prosthetics for bionic limbs. I mean, we're talking about truly life-altering, independence-restoring technology here.
And we are seeing some incredible cutting-edge tools getting us there. Over at Stanford, they've developed NeuroRoots. It's this ultra-flexible, low-profile, implantable platform that causes very minimal damage to neural tissue, but still provides long-term stable recordings to help reverse paralysis. Then there are these protein-engineered nerve guidance conduits that are helping peripheral nerves actually regenerate. We're seeing bidirectional retinal prostheses being developed to restore vision, and institutions like MIT are creating highly engineered biointerfaces for bionic limbs. It really feels like the hardware is finally catching up to the clinical ambition.
Which leads us perfectly into Section 5, the neuroethics frontier, the cost of reading minds. Because with all of this world-shifting power comes a pretty profound question. Who exactly owns your neural data? As BCIs move out of the strictly regulated clinical space and start hitting the market as commercial, non-invasive consumer wearables, tech companies are suddenly gaining access to the raw electrical signals of your brain. Your attention span, your emotional state, your cognitive load, all of it is becoming measurable, and perhaps more worryingly, potentially monetizable.
This shift is forcing incredibly urgent policy discussions worldwide right now. We are having to grapple with neural data privacy. Like, how is this deeply intimate information actually stored and protected? Then there's the whole concept of cognitive liberty, the fundamental philosophical right to mental privacy and self-determination. We also have to figure out informed consent in these new consumer markets. Are everyday users truly aware of what they're giving away when they strap on a fancy EEG headset just to try and optimize their workday? Honestly, regulators are scrambling to build these frameworks as we speak.
Our source material reframes our current reality pretty perfectly. It points out every newsletter you subscribe to is a channel of information flowing into your brain. You're building an interface. And it's so true. In a lot of ways, our modern digital consumption already mimics the basic framework of a brain-computer interface. You curate the channels you want, you allocate the mental bandwidth, and your brain processes the inputs. Consumer BCIs, well, they're really just going to remove the physical friction of a screen or a keyboard from that exact same loop.
Which leaves us with this final kind of provocative thought to chew on. How will you navigate a world where your inbox is literally a brain-computer interface? A world where the barrier between the collective digital knowledge of the internet and your own personal neural network is completely dissolved. The mechanics of neural decoding are already here, folks, and they are advancing by the day. Thank you so much for joining me on this explainer. Keep learning, stay curious, and I will see you next time.